All right, can you hear me? Yeah, okay, it works. Welcome everyone. So today we have the pleasure to have Wang, who is professor at Ohio State University. He's expert in techniques to do exoplanet imaging and in exoplanet science. So obtained his PhD in 2012 from Florida State University. Then he did a postdoc in Yale, one in Caltech, and since 2018 he's a professor at Ohio State University. So
Thank you, Denise, and it is a great pleasure to be here, and there is a mistake to be corrected. I get my PhD at University of Florida, not Florida State. Those two are big rivalries with each other. So that is, I have to correct for that. But in any case, I really enjoyed Leuven, the city of Leuven, and I really thoroughly appreciate the opportunity to come here to collaborate with Dini and also to see the Department of Astronomy here. And today I will talk to you about one aspect of my research, which is on the instrumentation front. It's multi-aperture fiber nulling. And the goal of this technique is to study the atmospheres of exoplanet and hopefully one day to search for the biosignatures in the atmosphere. So we'll start with this figure that nobody will skip in an exoplanet talk. So what you are seeing here is a planet mass versus semi-major axis. So I only show two populations of planet here. The first population in blue is the planet detected by radial velocity, and the population in red is a planet detected by direct imaging. And the purpose of showing this figure is to show you that these two populations are almost touching each other, meaning that some of the planet may be suitable by both techniques. And because they can detect it by both radial velocity and direct imaging, there is very rich information to be extracted for the planet that can be studied by both techniques. Another thing to add, which is also a new development, which is Gaia, the proud of the European people here, because Gaia is developed by ESA. And the Gaia also offered a great opportunity to detect giant planet using astrometry, the wobbling of the star in the sky plane. So I'm showing you one example of the lowest mass planet that detected and confirmed by Gaia. So this AF loop B here. So with the combination of radial velocity direct imaging and astrometry, we can actually study those planets in very, very details. And the story does not end there, right? Because the synergy between the radial velocity and the direct imaging also extend to the study of habitable planets. The reason is that, if for planets around stars of different masses, right, that their habitable zone also change as a function of stellar masses. For the solar type stars, the habitable zone is around 1 AU, and for M stars, the habitable zone is 1.1 AU. So for those planets in the habitable zone of low mass stars of M stars, the orbital period is usually like 10 days or 15 days, and they are short enough to be detected by radial velocity, because radial velocity is sensitive to short period planet. And with the advent of ELTs, which provide a high angular resolution imaging, those habitable planets around M stars can also be detected or potentially detected by direct imaging. So you can actually study the habitable planets around M stars using both techniques. I will explain in more detail why that is the case. So I'll go back this plot, but what I show here is, again, there are two populations, right? All planet detected by radial velocity, and the red is the planet around FGK stars, the solar type stars. And I also mark the habitable zone in this black box, or the box defined by the black line here. What you can see here is that with radial velocity on solar type stars, we don't really have any planets in the habitable zone. And the answer is obvious, which is that those habitable planets around solar-type stars, Earth as an example, takes 365 days orbiting around the solar-type stars. And we don't have that baseline and also the sensitivity to detect a habitable planet around the solar-type stars. But the story is different if we look at the planet or habitable planet around M stars. So with the recent radial velocity discoveries, many of them, as you can see, falls into the habitable zone. This is again because the planets in the habitable zone around M stars, they have a shorter period, and they also have a higher radial velocity signal to be detected. So that's why we have many habitable planet candidates detected by radial velocity. And they can also be studied by direct imaging, and I'll explain why in the next slide. So how do we directly study or image those rocky planets in the habitable zone? So here I plot in different dimensions. On the y-axis here, you can see it's on the contrast. Contrast is defined by the flux ratio between the planet and the star. And 10 to minus 6 means that the planet is 1,000,000 times fainter than the host star. And 10 to minus 7 is the planet is 10 million times fainter than the host star. So I also marked all the nearby planets around M stars in blue, which are the targets in the south, and the red, which is targets in the north. As you can see that many of such planets, they have a contrast somewhere between 10 to minus 6 and 10 to minus 7, and also their angular separation from their host star is on the order of millisecond, 10 milliarcsecond. Right? If you think about it, it's very small angular separation to be detected from ground. Usually the seeing is 1 arcsecond for observers, right? If you are at the ESO, like in the La Palma side or in the Chile side, the seeing is usually 0.5 arcsecond, but it won't get you to this 10 milliarcsecond angular resolution. So you will need a very high spatial resolution to resolve the planet from their host star. So you're facing two issues there, right? There is one opportunity, but the two potential issues. The opportunity is that for those planets in the habitable zone around M stars, you could study both using radial velocity and the direct imaging. Radial velocity will tell you the mass, and the direct imaging will tell you the chemical composition. And the combination of the two will provide a very powerful constraint on what type of planet and what on their atmosphere and the interior structure. But the challenge is that those planets, they're really faint around compared to their host stars, right? They are 1,000,000 times or 10 million times fainter. But they also their angular resolution is about 1 lambda over d. Here the lambda is wavelength and the d is the aperture of the telescope. You really required a telescope size of 10 meters and bigger to spatially resolve those planets from their host stars. So those are the challenges that we are facing, right? The contrast and the angular separation. So how do we overcome those two challenges? So one potential solution is what I call a high dispersion coronagraphy. We need both high contrast imaging and high resolution spectroscopy to directly study those planets. How does it work? So we start from left to right. On the left, you see a very blurred image of a planetary system. But in that image on the left, you are not going to see the planet because you are seeing limited, right? And then you have the planet that is 1,000,000 times fainter. So there's no way you can see the image. Only after you directly image this system using adaptive optics and pass the light through the coronagraph. What is a coronagraph? Some of you may know, some of you may not. Coronagraph is a device with which we suppress the starlight and allow the planet light to go through. So the coronagraph will does the job so that the starlight will be attenuated by a fact of 10,000 or 100,000 times. But it's still not quite enough, right? Recall that the planet is 1,000,000 times fainter, and the coronagraph only reduced the light by about 100,000 times. So the planet light still buried in these residual images here, which is the one that after coronagraph. So how do we further separate the planet light from the starlight? We have to resort to the different information content. For example, the planet will have a different radial velocity from the star, and the planet will have the different chemical composition from the star. So we have to use those information to further separate the planet signal from the star signal. So on the right-hand side, this is how we reduce the data. You have a very noisy spectrum of the planet because the planet light is still overwhelmed by the starlight. For every photon that we receive from the planet, there's about 10 or 100 photons from the star. So the planet light is still buried under the noise level. So we have to need the cross-correlation technique. What is cross-correlation technique? You have to devise some sort of template. For example, in this case, a template of oxygen, right? And then you cross-correlate that noiseless oxygen template with the very noisy spectrum. And the product is a cross-correlation function, which is on the right. So if you see the match between the template that you're using and the noisy spectra, you expect to have a peak in the cross-correlation function. So that tells you that you detect such species. In this case, is oxygen. You can replace the template with CO or CO2 or water template. So in this way, you can detect the planet using cross-correlation. And that is the whole idea of high dispersion coronagraphy. So HDC, short for high dispersion coronagraphy, can help you to improve the contrast and also help you to improve the contrast by a factor of 10 or 100, which allows us to directly study the planets around M stars. So here is a schematic. Here what you see is again contrast versus angular separation, right? And I also color-coded a different data point. The red data point are planets around M stars. You can see that they are very close to their host star, and also they have a contrast about 10 to minus 7, roughly there. So the ELTs, for example, the European ELT, extremely large telescope, which has a diameter about 40 meters, will improve the angular separation, such that 1 lambda over d correspond to about 10 milliarcsecond at 2 micron, 1 to 2 micron. But HDC will bring down the contrast so that you can directly image and study this planet around M stars. So HDC not only works for ground-based telescope, it also helps you to improve the contrast for space-based missions. The next generation, for example, HABEX or LUVOIR that is under study by NASA, right? Currently, the high contrast imaging test bed can only reach about 10 to minus 9 contrast level for space mission. But it really requires a 10 to minus 10 contrast to directly study a true Earth analog, which is an Earth-like planet around the solar-type stars. So HDC can help to gain the contrast, the gap, for both ground-based telescope and the space-based mission. So I give you some broad or big pictures pitch to why it's important to study exoplanet using both high contrast imaging and high resolution spectroscopy. So what is the roadmap? How do we eventually achieve that? That it will be the meat of today's talk. So I broke that roadmap into few steps. Okay, first one is benchmark brown dwarf, which I will skip in today's talk for the interest of time because I don't think I have sufficient time to go through this step. So broadly speaking, and to be very brief, so we need to first apply high contrast HDC or high dispersion chronography on brown dwarf, for which we know the ground truth. What is the ground truth? The ground truth is that the brown dwarf form in a similar fashion as the stars. If we were to apply this technique and study the chemical composition of brown dwarf orbiting around solar-type stars, we should get the same chemical composition or very similar chemical composition from the brown dwarf atmosphere compared to the solar-type star, host star, or the primary stars. So this should be the test that we have to complete in order to move on to the next step. And the next step would be the single-aperture fiber nulling. Okay, and this is, I will explain in the next few slides why that is the case and how that is achieved. So, fiber nuller. Okay, what is a fiber nuller? So, from the description, you know that it evolved a fiber, right? In this case, it's a single mode fiber, short for SMF. And the nuller is that you have to, you will need to null the starlight. So basically to suppress the starlight. So it's another form of chronography. So I also, in this illustration, I brought that into 3 categories. So first one is what we call stellar spectroscopy. In this case, is that the planet and the star, both the planet light and the starlight will go into the single mode fiber. And this is the technique that we usually use to study the transiting planet, right, where you have the starlight and the planet light, and there's no way for you to separate the two, because the transiting planet, they have very short orbital period, and the angular separation is too small to be spatially resolved by telescope of any size. So this is mainly used for transmission spectroscopy at a high resolution. And what we normally do, and in current state of the art, is that if you can spatially separate the star and the planet by a lot I mean a few nm/d. This is, you know, what GPI and the Sphere are doing. Those are state-of-the-art high-contrast imaging instruments. They can study the planet by spatially separate them, few nm/d, and using low-resolution spectroscopy to characterize the planet atmosphere. The one I'm trying to focus and also bring to attention is this intermediate case where you have, you know, you can only resolve the planet at about 1 nm/d. And that is the kind of spot that a current chronograph cannot perform, because their current chronograph, they can only operate at a few nm/d, and their contrast will not be great at 1 nm/d. So this is the place where it requires or need the fiber nuller. So how it works is that you have the planet and the starlight separated by about 1 nm/d. And you put a single mode fiber on axis. So that is to the right of the plot. And in order to cancel the starlight, you have to modulate the phase of photons coming from the stars. In this case, it's using a Vortex plate, wave plate. What it does is that it will modulate the phase of the photon azimuthally, meaning that going around the position angle from 0 to 360, the phase is also changing by 2 pi. So this is what the rainbow color means here. And to quite counterintuitively, if you focus the light on the single mode fiber with the phase modulated by this wave plate, Vortex wave plate, the end result is the total suppression of the on-axis light. And to explain that, you could imagine, you know, in a less complicated case, in a Young's double slit interference, right? You have 2 slits, and then you interfere the light coming from the 2 slits. You will get constructive fringe in the middle, right? That's the famous Young's double slit interference experiment. But if you could modulate or change the phase of one slit by pi, and the end result is that you're going to have a destructive fringe, meaning that you're going to have a null in the middle of the two slits. So in this case, right, you can imagine at every opposite point, for example, the top point of the Vortex coronagraph or Vortex plate at the bottom, there is always a phase of pi change. So the photons coming from this opposite point will be destructively interference. And the same is the case for every pair of photons as you rotate in the azimuthal angle. So that is how you achieve the on-axis suppression for the starlight, which is in red. But planet light is different. It will come in at a slightly different angle, which is at an angular separation about lambda over d. The planet will not experience this total phase destruction or destructive angle. So there will be certain light from the planet going into the single mode fiber and being dispersed if you use a back end high resolution spectrograph. So that is how the fiber Nuller is working at about 1 lambda over d. You modulate the phase using whatever device. In this case is a Vortex plate, and then you can suppress the on-axis starlight and allow the off-axis planet light to go through. But Vortex plate is not the only option here, right? There's this recent paper by Eugene Serabin, and he basically proposed, instead of a Vortex plate, which is at the bottom panel here, you can use all sorts of different manipulation at the pupil plane to change the phase to achieve the suppression of on-axis light. The simplest case is what they call the phase knife, right? You can put half of the aperture with a 0 phase shift and the other half of the aperture of pi phase shift. This is analogous to the Young's double slit experiment. So when you focus the light with that kind of pupil phase distribution, you're going to get a total suppression of starlight on axis while allowing the planet light to go through. And in between those phase knife case on the first row and the continuous Vortex mask at the bottom row, there's a lot of cases in between that you could experiment with. So this is the single aperture nulling. And the reason I brought up this idea is that there will be a high resolution spectrograph being built at OSU. This effort is led by Jonathan Cross, who used to be an instrument scientist at Notre Dame, and he moved to OSU and also brought the project. What iLocator does is a high resolution single mode fiber fed high resolution spectrograph at the resolution of 200,000, and it will be moving to LBT in sometime this year, and we commission. Hopefully, we'll have a complete commission process by the end of this year. So it work with adaptive optics and work with a single mode fiber. So what we're thinking is that right before you focus the light into a single mode fiber, which is the input of the instrument, we put a phase knife in front, so that not only we're going to have a suppression of starlight on axis, we also can disperse the light using iLocator. So with this concept, we can achieve the direct imaging and also high resolution spectroscopy of some of the exoplanets. So that will be the first step. The next step is about dual or multi-aperture fiber nulling, right? I talk about LBT. LBT is a large binocular telescope. Binocular means it has two apertures, right? The single aperture is 8.4 meter telescope, but the two apertures are separated by 23 meter baseline. So what we could do is, again, analogous to the Young's double slit experiment. we can use the two aperture of LBT and have one of the aperture phase shifted by pi, which is what you see in B here. And at the C, which is the focal plane, after you do the destructive interfering, you're going to see these destructive fringes. Right in the middle is where the starlight is. It's not surprising that the middle is dark because, after the phase modulation, the focal plane, where the star is null. But the planet, which is at about separation of lambda over B, in here B is the baseline of LBTI, which is 23 meters. And then you have the throughput, which means that the planet light can go through at a throughput about 35%, up to 35%. So this is a work that we have done with Kobe Jurgensen, who's now at the CFA, Harvard. So this two plot shows you that on the left is a traditional single aperture Vortex fiber Nuller, which give you about 20% up to 20% throughput. And on the right, if you focus on the green curve, which is the fiber Nuller, dual aperture fiber Nuller, which give you a throughput up to 35%. So the reason why we're thinking about it is because we have these two apertures separated by 23 meter baseline. This is the best that we can do before any ELTs coming online, right? We have European ELTs that will come online at the end of 2030, but for the ELTs in the northern hemisphere, which is TMT, who knows when that will be built, right? There's a political dispute on the mountain of Hawaii, and also the funding situation for TMT is still uncertain. So before that, LBTI remains the optical and the near-infrared facilities on ground that can deliver the highest angular resolution. So this is the rationale why we're thinking about this and trying to build an instrument for that. And I also have done some calculations to show that, okay, if you want to study those radio velocity detected gas giant planet, which are shown in blue and the red here, how much time does it take in both K and L band? So if you want to focus on those columns with the T here, which is the exposure time, for some of the planet, it takes less than 10 hours to reach a signal-to-noise ratio of 5 in detecting certain molecules in the planet atmospheres, right? 20 hours for GJ876, it's still manageable, but for those planets, that requires 400 hours, that's totally untractable. But for some of the directly radio velocity detected gas giant planet, we can actually use this technique to study their atmospheres. And the total exposure time, as explained by the equation here, include actually the noise sources of detector, the background, and also the finite size of the stars, if it's close enough and being spatially resolved. So that is for follow-up of directly detected gas giant planet. And another application for this concept would be the search of planets in the debris disk systems. And why we're trying to do that? This is because, for the blind search, which is the strategy for sphere and the GPI, the yield, planet detection yield, is usually 1 out of 100. You have to survey 100 stars in order to detect one gas giant. But a study led by Tiffany Mascott and also along with other papers, show that if you have a presence of debris disks, so those debris disks can be a signpost of planets. So if you focus those systems with debris disks, the planet yield could be improved by a factor of 10. So meaning that if you surveyed 100 stars, you can yield the 10 planets. So why we cannot do it now is because if you want most of the time, those planets, they tend to be around they form around ice lines, right? Water ice lines, CO ice lines. but the ice lines around those nearby stars tend to be very close to their host star. So here I just show you an image to give you some ideas how challenging is it to directly search those planets in the debris disk systems. So I'm showing you, so all those annular structures are the Hubble images of a debris disk system, right? But the planet that we're trying to search for are actually in this ring, like marked by the white circle that is at the very center of the image. So that is the LBTI resolution that we can push in, which cannot be accessed by either JWST or Hubble Space Telescopes. So this will give us the niche of detecting those planets in the debris disk systems. So where we are at. So this, I'll show you a few pictures of the lab setup for which we simulate the LBTI. You know, as you can see, the light comes from the bottom right. So it comes from a single mode fiber and being collimated by off-axis OAP, off-axis parabola. And then we'll use a deformal mirror to reduce the waveform error. And the light will go to two paths, path 1 and path 2. Those two paths will emulate the LBT setup. And then we focus the light into a single mode fiber. So we use this system trying to study the dual aperture concept and to see how that is affected by wavefront aberrations. So we first started with a single aperture, try to reproduce the Vortex fiber Nuller. So on the left-hand side, you see this is a theoretical throughput. What is important is that you can see that the throughput reaches highest at about 1 lambda over d. On the right-hand side, this is our lab result to showing the throughput as a function of angular separation here. And you can see, on both sides, the throughput is the highest around 1 lambda over d. This is similar or exactly the same as predicted by theory. But you see this asymmetric peak in the throughput. That is due to the static aberration in the system for which we're trying to correct for. So now the wavefront error is about 40 nanometers, and we're trying to get down to about 20 nanometers. And to do that, we have to involve some wavefront sensing and the correction techniques. So this is a work in progress by my grad student Anusha Pai, who's supported by a NASA grant to conduct the experiment. So we're doing some fun experiments. So in order to correct or control the wavefront, we need to correct or control the deformable mirror. So here is one fun exercise that Anusha produced, OHIO, using the deformable mirror, try to poke the different actuators. And OHIO is Ohio, just in case you have not realized that. So this is where we are. So we are being able to reproduce the dual aperture, the Vortex fiber Nuller result to some extent, but we're still limited by aberration. To go further, right? Go further or go beyond the single aperture, we also would like to conduct some dual aperture experiment. And this is something that we are doing in collaboration with Caltech, which has a high contrast imaging test bed. So what we're trying to do here is instead of creating two paths that are using a beam splitter, so now we create the two paths using an aperture mask, which is shown on the top right. And we put this aperture mask in the optical system to create fringes. And the fringe that we're producing here is null fringes. And the null is achieved by changing the DM actuator height, right? So as you can see, that changing the phase is equivalent to changing the actuator length. If you change the actuator by lambda over 2, then you will achieve the phase change of pi. So on the left, you see the null in the center, and the two bright fringes is actually the throughput of the planet light. So if you were to plot in a more graphic form, which is on the right-hand side here. So we show two things. The red is a theoretical prediction, which is give you throughput about 70.5%, and the reason is this is not at a 35% is because we're using a rounded shape single mode fiber, right? The 35% throughput will be achieved if you use some to change the PSF to match the mode of the single mode fiber. So red is theoretical prediction, and the black is what we achieve in the lab. So if you look at the inlet of the plot, that tells you, what is the deepest now. So for now, the deepest now is at about 1 out of 1,000. So the now is about 0.1%. This is as good as we can achieve in the lab with monolithic light and DM phase modulation. So that is what we have achieved now. The next step would be moving on to demonstrate the white light and also to further improve the now using with improvement to reduce the wavefront errors in the optical system. So 0.1% may not be impressive, but if you think about this is the now at a 0.1%, right? But there is also another improvement of contrast brought by high resolution spectroscopy, which is another factor of 10 on 100. So actually with this system, you can actually study the planet that is about 100,000 times fainter than a host star, which there are many of them that can be studied. So the next step, okay, in a roadmap is multi-aperture fiber nulling. So we go from 2 aperture to multi-apertures, and we discussed this in our paper in 2020. So on the left-hand side is illustration of how you can use a Vortex fiber nuller on GMT, which is a Giant Magellan Telescope, another ELTs that will be built in Chile, right? So left is the pupil plane, right? You have this 7 sub-apertures. Each sub-aperture is 0.5 meters across, and then on top of it, you put a Vortex plate. And on the right-hand side, this is the PSF you are going to achieve. In the center, that's the starlight, totally null, and around it, that's the throughput of the planet. So similarly, you can also modulate the piston of each sub-aperture or put a mask, that aperture mask that change the phase of each sub-aperture by, in this case, pi/3, so that around the circular apertures, you achieve this phase shift of 2 pi. And you can see that the end PSF or the throughput is very similar to a Vortex nuller. So on the surface, on the face value, there are a lot of techniques that can be done, right, to suppress the stars. But which one is better? What is their sensitivity to wavefront aberration? And which is, there are a lot of trade-off, and also the understanding between the theoretical performance and the realistic performance that needs to be done. And that is why we try to build the simulator for ELTs. Here, this is the same system that I showed you earlier, but with the upgrade that will be identified in the red mark. So eventually, we want to replace the DM systems in our optical system from currently 140 actuators to 1,000 actuators. Once we make that update, we can change the aperture to simulate, for example, TMT and the ELT and GMTs, so that we can study do a comparative study of different techniques to understand their realistic performance. For example, with the bandwidth, for example, in the presence of aberration in the system. So that will be what we'll be doing in the next few years. And before I conclude, I will also advertise our imaging science lab at OSU, because not many of you are aware that that we have a very strong team to build instrument, and we have an excellent track record for the past 3 decades. We deliver a lot of very impressive instruments. The DESI dark energy survey instrument, which is actually currently operation at the Kitt Peak Observatory, and it's being used to take millions of spectra of nearby galaxies to understand the expansion of the universe, and also trying to understand what is the origin of dark energy. So that's one example, and another example that we have is a KMT instrument, which is the one that produced so far the most microlensing detections. And at the very bottom is the MOD spectrograph, is a power horse instrument operating at LBT. So we hope to extend the excellent track record of OSU instrumentation teams with this new concept that I just introduced. Not only do I work on instrumentation, I also, with my team, work on many scientific investigations on exoplanet. So here again, I show you the mass versus semi-major axis plot, and I also put my students' headshot, and including mine too, on different parameter space. As you can see, the research actually spans on all populations of exoplanet. And the very top left is the hot Jupiters. So we studied the wind and the chemical composition of hot Jupiters with the Pepsi. And this is the work led by, again, Anusha. She is actually work at the interface of science and instrumentation. And my student, Kirsten Bowley, who's doing the test survey to understand planet formation around the very metal poor stars. And Marshall Johnson is leading a NASA-funded program to study the cold Jupiter migration and their eccentricity and obliquity distributions. So if you look at the top right part, that is a project led by me. We are trying to using the C2O ratio to understand planet formation, and also provide some cautionary tales of using C2O to study the planet formation. I have a lot to say about the caveat of how much conclusion you can draw just by using C2O ratios. So if you're interested in that, please talk to me. And Michael Plummer is my grad student who is using to simulate the ELT performance to understand the surfacing homogeneity of ultra-cool object. And the reason is that, with the ELT, we can study the surface structures of brown dwarf and the M stars, and by studying them, we can understand, what is the spot of magnetism on M stars, and how that would affect the habitability of planets around M stars. If you're marching down the mass direction, you see Caprice Phillips, who is trying to use JWST to search for biosignatures of nearby gas dwarf planet. And in this case, the biosignature is not oxygen, is not water, not anything else but ammonia. And if you're interested in that, talk to me. And at the very bottom, we also have a grad student working on the interior structures of rocky planet. We're trying to build the modeling framework to understand their interior structures, and also to understand how observables such as radius and the mass could be used to model the interior structure in order to understand the core, the presence of the core, and also how that interact with the mantle to understand the necessary conditions for a habitable planet. So with that, I would like to conclude. I think I'm almost at the time limit. The conclusion is that now we're in the era of study the same planet with multiple techniques. I give you an example of radio velocity, direct imaging, and astrometry, right? But the problem that we are facing are very close separation between the planet and the star, and the high contrast between the planet and the star. And we're developing techniques to overcome those challenges. And among the solutions, the dual aperture fiber nuller or multi-aperture fiber nullers is one compelling candidate to address those challenges. And we are constantly looking for talent that could be joining our team. With that, I will thank you very much.
All right, thank you very much, Ji, for the very nice talk. Is there any questions?
Yes, thank you very much for this talk. I have a question on the spectral resolution you're choosing for the HDC technique, because if I remember, if you're increasing the spectral resolution you have, you get more spectral information on the exoplanets, so the cross correlation techniques works better. But then you get less photons per pixel, so then the dark current is getting more and more powerful, and the readout noise also. So what is the most optimal spectral resolution that you are calculating?
Yeah, so this is a very good point, and in our paper 2017, we kind of break this question into two parts. One part for ground-based telescope, the other part for space-based telescope. And for ground-based telescope, because you have a much larger aperture, you can afford to spread the photon into many spectral channels. This is less of a challenge for ground-based observation. But for space missions, it is significantly affected by detector noise, such as dark and readout noise. So the optimal resolution is on the order of a few thousand. But for ground, it is at about 100,000. And also, another things that could change the conclusion would be, the intrinsic broadening of the planet spectrum, right? Because there could be rotation, could be, thermal broadening of the planet, or collisional induced broadening of the planet atmosphere. If the planet atmosphere does not produce the very sharp spectrum, there's no need to go to very high spectral resolution, because your intrinsic spectrum is already broadened.
Thank you very much.
Hello, thank you for this talk. I was wondering, you talked about this two aperture mask method, and I was just wondering, isn't there any light loss in that process compared to other techniques?
Yes, of course, for everything you gain, you lose something, right? You gain, in this case, the stability of the wavefront, because from a single aperture, if you put an aperture mask, then the wavefront will be the same or similar, right? There is no need for compensate for path difference as a traditional interferometry technique. However, you lose the photon because you're masking out the majority of the photon. The solution, however, as I pointed out in one of the slides, you could using this face mask or the face knife technique, right? In this case, you can imagine having a face mask that covers the whole aperture, so that you do not lose any photon, as long as you can modulate the photons using, for example, the liquid crystal technique. And you can also achieve the broadband in this case.
Other questions?
Thank you for this great talk. I was wondering, it looks like this idea of using a phase knife on eye locator rate, this is already well underway, right?
Already
way underway, right? So I was wondering what spectral range you hope to do this over, and what type of technology you use to produce achromatic phase shift with that.
Yeah, so for iLocator, it works on Y and the J band. So I think it's uncovered 0.9 to 1.2 micron. And what are the other questions? Sorry.
what technology for achromatic phase shifts?
I don't quite understand. Can you repeat?
Yeah, so in order to have a deep null over a broad range, you need to produce a pi phase shift, right? And if you try to do that with a piston, it won't be achromatic. So is there, like, what technique do you
Right.
do?
So I think the bandwidth depends on what technology you use to achieve the phase shift. If you use a piston, then it will be very narrow bandwidth, because half phase shift for one wavelength is not half phase shift for another wavelength. However, I think if you use this broadband wave plate, for example, with some of the liquid crystal technology, that could achieve 5 to 10% bandwidth, which is sufficient for some of the science. So one science application that we're thinking about is to use this phase knife plus eye locator to study some Gaia detected multiple star systems, right? Because Gaia could result in some astrometry discoveries of close binaries. Sometimes could be an M star around very massive stars. So we're thinking about using this phase knife plus eye locator to directly detect those low mass companion around massive stars, trying to understand their orbital architectures, which will be very important to understand binary and the multiple star formation.
Other questions? So G will stay with us until mid-July. So if you have more questions, he will be around office 3 or 4. And we can thank him again.
Thank you. My computer survived.
Yeah.